Hello, everybody. Good morning.
Nima.
So, yeah, so we're on to my class, and my part for my part. So, yeah, so for my part, I have to close the YouTube. What do I do then? So for my path, this is what we are going to be taking. We're going to be taking acid-base salt, and then now in this lecture today we must cover acid-base salts. And in our next lecture, we'll be looking at redox titration and a little on electrochemistry. And I'll be running fast because we just have 2 lectures to complete this. But I know that everybody has eaten food since we were born to today. If none of us have eaten, probably would have died at birth. So all of you in this class have eaten food since you were born. And the food you've eaten had different tastes. Some of the food you ate were sweet, some were sour, some are bitter, some are salty. Even this morning, many of you have eaten. Many of you have eaten. Even if you are on Lenten season, at least you ate last night. Even if you are doing Ramadan fast, at least raw, you put tiny something in your mouth, small something in your mouth very early in the morning. Itunu awe. You have done itunu awe. I hope I'm saying the right thing, Sha. But anyway, the message is gotten. And whenever you taste whatever you ate, when last you ate, had a taste, either sweet, sour, bitter. So these are the 4 major classes of tastes. Any food you eat can be classified in. Some food are sweet, sour, sweet, bitter, salty, sour. Some foods are different, but food fall into this classification.
Timothy.
I said, all the food we've eaten, that's the taste. And so, please mute yourself. So, in chemistry, the reagents, the things we work with, can generally be classified as acid, bases, or salts. Acids, bases, or salt, although there are other classifications. But primarily, anything you use can either be acidic, basic, or neutral. Neutral in terms of, yes, neutral. And then we have another class of things we call salts. And so, want to look at this classification based on acidity. So once there are three main classification of substances based on the acidity, or there are three main classifications. There are three main descriptions. Sorry, there are three main definitions of acids or bases. We have the Arrhenius classification, the Brostolowitz classification, and the Lewis classification. We'll be looking at them. So the Arrhenius classification tells us that an acid is anything that produces the H plus ion in solution, while a base is anything that produces the OH minus ion in solution. So, according to the Arrhenius acid, hydrogen concentration are usually present in water. When trying to explain the concept, he says hydrogen ions are usually present in water. And in water, this hydrogen ion, if it's an acidic medium, the hydrogen ion will attack the water to form the hydronium ion. And that is what we've written. So, but it's allowed to write H plus in chemistry, but actually what is actually happening is the hydronium ion that reacts to give us that acidic property. Then we have a base. Base is anything that adds on an OH, and that's what happens. And conjugate base. Now, this hydrogen ion is reacting with the water molecule to give us the hydronium ion. So in this reaction, the water is acting as a conjugate base. Water is acting as a conjugate base, while the hydrogen ion is acting. Please mute yourself. Don't let me don't distract me. Don't let me have to always go and mute everybody. It will delay our class. We don't have time. Please, and don't let me have to single you out and call your name. It might come with some penalty. Please don't let's do that. Let's remain friends. So the water molecule here is our conjugate base, while the hydrogen ion is the acid. So for every acid, you would always have a conjugate base. Like I said, the hydrogen ion we still allowed to write H plus. But what is actually happening that gives us that acidic feel is when hydrogen ion reacts with the water molecule to give us the hydronium ion. But there's a limitation of this Arrhenius theory. One, there are limitations which you should know. Limitation is that the hydrogen ion or the hydronium ion or the OH must be released or accepted by a base. That is, for example, hydronium ion must be released by an acid. OH ion must be released by bases. But this does not account for weak bases. That's the problem. So how do you account for the basicity or the acidity of ammonia gas in the presence of water? So ammonium gas in the presence of water releases OH ion, hydroxide ion. It releases the OH ion in solution, but it does not have OH in its original thing. See, ammonium is NH3, but in water it releases the OH ion. But yet in its molecule it doesn't have OH. Unlike sodium hydroxide, in the molecule it has OH, so it can release the OH. How do you give what you don't have? So the Arrhenius theory limitation does not account for it. Well, it overemphasizes that all base must be able to release OH. All acid must release OH, and you will find all acid must release H plus or the hydronium ion. All base must release the OH, and you usually will see these things in their molecule. But for ammonium gas, it doesn't have any OH, so it doesn't explain for how it releases the OH ion in water. It doesn't explain that. So that's the one limitation. There are many more limitations with the Arrhenius theory. The Arrhenius theory says that So the number one limitation, which I've already explained, the presence of water is absolutely necessary for an acid, for acid and bases. Before any substance becomes an acid or base, there must be water present. But dry HCl also acts as an acid, so it cannot explain how it acts as an acid. It does not explain the acidic and basic character of substance in non-aqueous substance. There are some non-aqueous substances that are not in water. They are in liquid but not water, and they still show the acidic basis, the acidic and basic property. So Arrhenius theory does not explain that. The neutralization process is only possible in aqueous solution. But how about in solution involving salts? That is, neutralization will only happen when we have an acid or a base. It does not account for neutralization that involves salts, that forms salt in the absence of a solvent. So that's the problem. The acidic character of some salts also, it does not explain the acidic character of some salts like aluminum chloride in aqueous solution. It can't explain, but we all know that's an acid. That salt gives us acidic properties, but it can't explain it. And it cannot explain this. So in fact, to explain for ammonium, it has a strange artificial explanation for ammonia gas. So these are the limitations. These 6 things are the limitation of the Arrhenius theory. I can ask you to tell me the limitation of the Arrhenius theory. So you should be able to tell me in an exam the limitation of the Arrhenius theory. Arrhenius theory, there are 3 theories on acid and base. We have the Arrhenius theory, the Lewis theory, and the Bristol-Lewis theory. Arrhenius theory is one of the early theories. It tells us, it explains well how things become acid by either accepting a hydrogen ion or giving out OH, but that's how it becomes a base. And it says that in accepting, in releasing this hydrogen ion, this hydrogen ion usually reacts with a water molecule to form the hydronium ion. Anything that can do this, that can release a hydrogen ion that will react with water to form the hydrogen ion, is an acid. And a base, anything that releases the OH minus ion, is a base. Anything that falls short of that definition is not an acid, according to the Arrhenius theory. And I've shown you 6 limitations of the Arrhenius theory. We want to look at it to further understand. So, for example, look at this ammonia reacting with this in gaseous state. I told you it doesn't explain for gaseous substances. Let's go over to the Bristol-Lewis theory. Bristol-Lewis theory says acid, or Bristol-Lewis definition of acid and base. Now, I want to look at the acid one by one. A proton is anything, an acid is a proton donor. Once it releases a proton, it is an acid, just like the Lewis theory. While the base is anything that accepts a proton or decreases the proton concentration when it dissociates in water to give the OH. So this is the definition. It's slightly more detailed than the Arrhenius theory. Arrhenius theory says it gives out OH, finish. Or it gives H plus ion to react with water. But here, this one goes a little more detailed. It says it releases a proton ion or leads to an increase in the concentration of proton ion when it dissociates in water. It's similar, the acid definition is similar, but it added the clause of increase in the concentration of proton ion once it dissociates in water. Why Bristol-Lewis theory is say anything that decreases the hydrogen concentration when it dissociates to give the OH is a base. And so it now explains for substances like sodium fluoride. It's a basic salt. It's a basic salt. So when you dissolve this in water, it releases the OH. Releases a OH to form HF and OH ion. Sodium hydroxide speaking is not a Bristol-Lewis base, because if you use sodium ion, strictly speaking, is not a Bristol-Lewis base because it cannot accept a hydrogen plus, but it releases a OH minus, which when it ionizes is a brostolorist gas and can accept hydrogen ion. So you see, we are trying to explain it with respect to brostolorist acid and base. Here, sodium hydroxide, if you just look at sodium hydroxide, it only fulfills the law of Arrhenius ion, just looking at it on the surface level. But if it reacts in water, it will react with the water molecule and reduce the hydrogen ion there. So based on that, it has fulfilled the condition of being a Lowry's acid, but he has to first dissolve in water to obey the Brustad-Lowry's theory. Here, sodium fluoride, the Brustad-Lowry's theory has helped us explain how sodium fluoride is a basic salt. But if you use the Arrhenius theory before, you would have been able to explain how sodium fluoride is a basic salt, because it doesn't give room for such explanation. There's a term I need to explain to you, acid dissociation. Ha to give me A minus plus H plus. When acid dissociates, it gives you a conjugate acid, a conjugate base, and its hydrogen ion. When acids dissociate, you always have a conjugate base and its hydrogen ion or hydronium ion, as the case may be. And so if that, our constant is always product over reactant, equilibrium constant. There are different types of equilibrium constant, K ionization, K neutralization, there are all sorts of constants in physical chemistry. But one thing that is common to them is that when you hear anything constant, it's always product over reactant. So now this is constant of ionization. For any reaction, we can most times have a kind of constant. So, but you call the constant related to that kind of reaction that was taking place. So here, this is an acid ionization. So we say K ionization. We say with K acid ionization, we say product over reactant. With base too, when a base dissociates, when a base reacts in water, it will give its conjugate acid and its OH minus ion. A base, when dissolves in water, when it dissolves in water, will always give you its conjugate acid and its OH minus. So I've introduced a new concept. The Brustad-Lowry's theory helps us to be able to talk about conjugate ions of conjugate bases and conjugate acid. We couldn't have talked about conjugate acid and conjugate bases in Arrhenius theory. So the good thing about Brustad-Lowry's theory, we're able to bring in new concept that helps us explain difficult situations in chemistry. And because of the conjugate acid and conjugate base explanation, we're able to explain equilibrium of ionization. We're able to talk about equilibrium of ionization, K ionization, and we're able to talk about pH, P, the log of concentration of ions. So Brustad-Lowry's theory opened a new field in physical chemistry, which helps us to do a lot of things and solve a lot of complex chemical situations. I've explained all this. So every acid has a conjugate base. Every base has a conjugate acid. And Brustad-Lowry's theory is what enables us to understand this concept. If an acid is strong, the conjugate base cannot be measured. Anyway, look at this equation now. Cn minus, those of you that are in the Zoom link, look at this equation, Cn minus plus H2 as in water, give us this. Can you identify the conjugate, which of these is the conjugate base? Okay, for this, which of these is conjugate acid? And for ammonia, where is its conjugate? Ammonium is a base, so where is its conjugate acid?
Ammonium ion.
Okay, then let me rephrase that question. I want to know the conjugate pair for this. Oh, sorry, there are two different questions. I thought I put the OBJ, sorry. So question one, answer me directly. I put the OBJ. I thought this was the base, but when I looked at it, it's not the OBJ. So yes. So which is the conjugate acid? Since this is giving us a basic something, which is the conjugate acid here?
Hydrogen cyanide.
Hydrogen cyanide is the conjugate acid.
Hydrogen cyanide will be the
Yeah.
conjugate acid here. Yes, hydrogen cyanide. So the pair is CnHCN. That's the pair here. What's the pair here?
For the conjugate base in the ammonium and the hydrogen fluoride.
This will be the conjugate acid. Ammonia is the conjugate acid here. Why this is the basic part. So the pair will be ammonium 3, NH3 to NH4 plus. That's the pair. That's the acid base pair here. Okay, which of the following does not constitute a conjugate acid base pair here?
I think it should be C.
Yes, it's correct.
Yeah.
Did you observe that the hydrogen is always increased in their pair, always increased by 1 hydrogen? Did you observe? So 1 hydrogen, 1 hydrogen. If we apply that theory, this is not. I'm trying to look for a simple formula for you but this is not, it's not always the same. It's not always the case. 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 But what you observe is that you always we are looking for conjugate acid base. You start with one of the entity, and by the time you get there, you see that it has HC, and yet it has anyway, the two will combine to give you the original, excluding the water. So if we combine this, it will give us the original excluding water. That's how you know it. So let's look at this. It fulfilled that rule. This one is this is a non-aqueous system. When you combine it together, it will give you this and this back. Anyway, we'll take C as the wrong answer, and I will confirm it to you soon. By the time we go further, you understand more. Now let's look at this set now. I tried to bring many examples. So look at this pair. H2, water and OH minus, a conjugate acid pair. Look at these two, they're a conjugate acid pair. These two, this increased by 1 hydrogen. They're a conjugate acid pair. These two, these are conjugate acid pair. It means that this half came from this. This half came from this. This appears, this appears, and this appears. So this is B. The answer is B. B is not a conjugate acid of this, because CO3 minus could not have come from this. If it dissociates, water will come out, or OH or something will come out. So it's not C. C is not the answer. B is the answer here. Which of these do not conjugate a acid-base pair? When you said C, I was not too sure, but now so there's always a trend. You always see that your conjugate acid or base came from this. There's no way CO3 minus will come from this. No, it will always lose either an hydrogen or oxygen or something. So the answer is B in this question. So we're right here, but for this B, for this second part, the answer is B. I hope everybody got me. Because this came from this, you can see the relationship. It came from this. This one hydrogen lost. It came from this. This you can see came from this. But this chemically cannot come from this. It will not just happen, see or no. It will either lose something, hydrogen with it. It will not just go stepwise. It will lose hydrogen with it or something. We'll not just go to this stage. Look at this HC. This it's one step, one hydrogen, and this will be a conjugate acid of the H2CO3. Did you get that? Look at this, one hydrogen, and this H2SO4 will be a conjugate to H2SO4. Did you get that? This HP4 is a conjugate to H2, and PO4 will be the conjugate to HPO4. I don't know if you got me. Look at this again. This lost one hydrogen to give this. When it's hydrogen, it's usually stepwise. When you listen to the slides again or my lecture again, you will understand what I said. But I need to move. But go over and listen to it and see my illustrations. Types of acid and base. We have monoprotic acid, polyprotic acid, polyprotic acid. Under poly, that is many hydrogens in the acid. Mono, only one hydrogen in the acid. And under the poly, we have 2 hydrogens, 3 hydrogens, 4 hydrogens, 5 hydrogens, 6 hydrogens in the acid. So when we have them, we call them polyprotic acid. So it means in a reaction, they can release this number of hydrogen in the solution where they are. We have weak acids and strong bases. So the Brostad-Lowry's theory helps us to be able to talk about conjugate acid, conjugate base, K of ionization, that's the equilibrium constant of ionization. It helps us to be able to talk about weak acids, weak bases, weak electrolytes, and poor conductors of electricity. Because by the way it explains acidity and basicity, we are able to account for some of these properties of acids and bases. For example, I told you of autoionization. I told you of acid ionization and basic ionization. And so based on that, because it explained it, we're able to write equilibrium constant of ionization. Now, also because Brostad-Lowry's theory accounts for H2 going to give us the H plus and OH minus, because those are anything that can increase the hydrogen ion, or reduce the hydrogen ion, even including giving out a OH minus, but it gives us an OH ion so that it reduces the hydrogen plus. We say it is a base. So because of this definition of acid and base, we can explain why water is made up of hydrogen plus and O plus. And we call this autoionization. And so based on Brostad-Lowry's theory, we can now say that water, when it undergoes autoionization, will give us the hydronium ion and the OH ion. So you see, Brostad-Lowry's theory has brought up a whole new concept and led to explanation of the pH scale. It helped us, it set the foundation for, because this is the principle, it's based on this ability to explain the hydrogen plus and the OH in water molecule. We could now account for the pH range, So look at this, Kw. So based on that, we can now say Kw is equal to the concentration of this and the concentration of this. We could explain that. We can derive all this theory. Now you need to know, I wanted to prove it. Let me see. I wanted to prove the theory. Let's see if I have time, because I must finish acid and base today. But you just need to know that Kw equilibrium for water, constant of equilibrium for water's autoionization, can be given as Ka times Kb. Kb, which is the same thing as the concentration of the hydronium ion times the concentration of the OH minus ion, which gives us, and for water, it is equal to 1 times 10 raised to the power minus 7. For hydronium ion, it is 1 times 10 raised to the power minus 7. For the OH ion, is 1 times 10 raised to the power minus 7. So when you multiply them together, when you put the Ka times Kb, you get your Kw as 1 times 10 raised to the power minus 14. Look at the, you know, when we wrote the equilibrium constant for the ionization of acid, we got that the conjugate acid, we got A minus concentration times H plus concentration over HA. We got this equation. And if we write the same thing for base, the ionization of base, we'll get this other equation. Kb is equal to this. If you write this, I'm trying to prove this equation on top now. If you write this, you get this. We can now say this times this will give me, so if we say this times this will give me this, if you cancel out the concentrations that are constant, we will get this. I'm just trying to tell you that this is related to this, and that's why we got this. In practice, neutral solution will have the hydrogen ion equal to the OH ion minus. In acidic solution, the hydrogen ions will, or the hydronium ions will be more than the OH hydroxide ion. Basic solution will have their hydroxide ion more than the hydronium ion. So once the concentration of the hydronium ion increases, OH ion will reduce, and vice versa. That's what this equation is trying to tell us. And we understood this concept from the Bronsted-Lewis theory. So if you play around with this equation, you must know this for your exam, this equation. You must know this equation for your exam. You must know this equation. You see these highlights? You must know it. If you are taking notes, write down that. It's a key thing. For many things you'll be doing with acidity, with basicity, with many calculations. It's key. It's something you would need. You need to know. And so we can prove all this. Now, this is a question, a sample question that we can try now. Calculate the concentration of hydroxide ion in a household cleaning solution of ammonia. Given this, calculate. I want you to copy this question, and in the next class, if there's time, one person will solve it. So yeah, look at this question and try and calculate it. Not in this class, maybe in the next class, because we are constrained of time. I only have two lectures with you. So concentration of hydroxide ion in a household cleaning solution of ammonium is this. Calculate the hydrogen plus ion. So you need this formula to do it. So you know that they said the calculation of H plus ion is this. So no, they said the calculation of hydroxide OH is this. So calculate the H plus is simple. You know the Kw is this. Kw, we know the Kw. You know the Kw. You know the H plus. H plus, we are told is 1 this. So what is the, oh, we are told the OH. So you use this equation. You substitute appropriately. Hydronium ion, we know is this. You substitute this here, and you find the concentration of your hydrogen ion in this solution. So if you use this equation, this same equation, this is the equation you use to solve this question. Just substitute this into this place, into the OH ion place. And you know your Kw is constant, 1 times 10 raised to the power minus 14. But you don't know this because in this solution, it is not the standard because we've changed the concentration of the hydrogen, of the hydrogen ion, so the H plus has reduced. The same principle is here. Calculate the concentration of the OH ion in a HCl solution, given that the hydrogen ion is this. So in this one is reverse. You know this, you don't know this. It's straightforward. I guess everybody in this class can solve it. No, I hope everybody in this class can solve it. Now, okay, so I've told you that we have a Bronsted-Lewis theory helps us understand the concept of strong acid, weak base, strong base, weak acid. It helps us understand those concepts. So because of that, we know that weak acids will not completely ionize, but strong acid will dissociate totally. Weak acid will not completely ionize, but strong acids and strong bases would completely ionize. And when something will go into complete ionization, we use this arrow. If it will not completely go into ionization, we use a reversible sign. So you see that the full one shows it goes to complete ionization. Whereas if it doesn't, in most physical chemistry, we use the reversible sign. They will put half, a small one under it. That will not be full. That will be in the other direction. So now a 1 molar solution of this contains 1 molar solution of H plus and 1 molar solution of this, and no undissociated HClO solution. That means this underwent complete ionization. So we have strong acid and weak acid. And we know them. You should know them. You should know them just by looking at them. Strong acid, weak acid. Weak acids produce weak conjugate bases. Strong acid will produce strong conjugate base. Acetic acid is a weak acid and its conjugate base is weak. And so that's that. Again, this our equation has come to play. Remember this equation where I said KB times Ka will give us our Kw. They just change the subject of formula. The same definition for strong acid, for strong base, weak base. It's still the Brustolowitz theory that helps us know all this. So you look at this, you should know this. Ammonia, all these are all weak bases, while these are strong bases. These are some examples. It's not exhaustive, but there are some weak bases and strong bases you should know. Like, for example, you should know sodium hydroxide is a strong base. KOH is a strong base. You should know ammonia, or even ammonia O, as in ammonium hydroxide, they are all weak bases. So we should know those common ones. Even if you bring OBJ, we won't bring the strange ones. No, we'll bring the ones that you normally use for titration, ones that you encounter every day, like especially for group 1 and group 2 elements. If an acid is did you see for weak acid and weak base, I told you we use the reversible sign to show that something is happening. But for strong acid, strong base, we just use one line to show it. So that's one key thing you must know. Let's look at this question. This is the only one applicable to this class. So this is not yet, I've not taught you this, and I won't teach you this. But this is 1 and 2 is what is applicable to our lecture. Calculate the pH of this and this and this. pH. You know, if you can calculate your K, you can calculate your pH. pH is minus log H. So we can calculate your minus log K. So pH is pH is equal to pKa. Let me take you back to the equation. So now this is this. Oh, I don't have it here. Anyway. Okay, pH, let me tell you from offhand then. pH is equal to pKa. pH is equal to pKa, which is equal to minus log the concentration of H, or your hydronium ion. So if you can find the concentration using this equation, using this equation, if you can find the concentration of this, then you can just say pH will now be equal to minus log of this. Then you can find it. You can find the pH of any solution. So that's the principle. That's how to solve this problem. But here now they say find the pH of this. You know, in this solution, it's not going to be hydrogen ion that is going to be more. This solution is going to be dominated by the OH ion. So to solve for this, you first find the OH concentration. The concentration of the OH ion are told as 0.2 molar solution of this. A solution of this, calculate the pH of this. So this solution now is barium hydroxide. You write the dissociation equation. This will give us 1 mole of barium hydroxide will give you 2 molecules of OH. So for every 1 mole, for every 0.2 mole of this, it means you get 2 times 0.0 mole dm cube of OH is equal to, okay, we don't have N is equal to CV. If we assume that the volume is 1,000 liters, you can find your N. Okay, it's concentration we need. We don't even need N. So if you find, so you already know your concentration. 2 times this will give you your concentration of OH. And if you find your concentration of OH, you put it in that equation that says that equation. You put it in this equation. I don't want to say it. Okay, you put it in this equation. When you put your OH in this equation, you know your Kw is a constant. You can find your concentration of acid, and that way you can solve that problem. I hope I solved it in this example. If not, in my next class, I'll bring it for you. But at least I've led you on how to solve it. Okay, look, I've even solved HCl. For HCl here, I told you, because it dissociates completely. So it means we'll have the same molecule. So you find your concentration of H minus log. You found that. For this, it's not as straightforward as that. You find your OH, look at it, you find your OH, and then you apply it. You can't use it totally. You can't minus log this. No, you have to invert it. So you know the scale is 14. This is another way to solve it. In the other way I was telling you to solve it, if you find it, you go use that formula, you get your hydrogen concentration, but this is simpler. You get your hydrogen concentration, then you do your minus log pH, minus log H to find your concentration. Another way is this way. So you find your concentration, you know that for every mole of this, you get 2 moles of this. So that's the concentration. You find the minus log, but this is for OH. OH is contributing this, but we are looking for pH. So pH concentration, the scale is 14. So that way you solve that problem. And so note that in both A and B, we neglected the concentration, the contribution of OH minus in the solution. Yes, it's hydrogen. We are looking at hydrogen ion concentration. That's what I'm trying to emphasize by what I'm saying here. In this, even though we got the concentration of OH, that's not what we're looking for. It's the concentration of hydrogen. When you hear pH, it's concentration of hydrogen is trying to estimate. So what is pH? That leads me on to pH. pH is the measure of acidity. Is a measure of acidity. It's not acidity in itself. It's just a measure of acidity, and it can be defined as minus log H. Minus log H is a scale of 1 to 14. It's a scale of 1, and it's related to this, our autoionization of water. Remember, in water, in neutral water, the concentration of hydrogen ion is this, and the concentration of OH ion is this. So if you put that concentration in, say, minus log H, you will get 7. Minus log this, you get another 7. So that is how the scale was arrived at. And it's one scientist that, okay, Soren is the one who came up with this idea. A simple way to express acidity. So he further simplified the Bronsted-Lowry's. He increased the application of the Bronsted-Lowry's theory. So Bronsted-Lowry's theory provided a foundation for the explanation of the pH scale. So Bronsted-Lowry's theory helped us to understand, to explain acidity of some things we could not explain, and basicity of some things we could not explain under the Arrhenius theory. It helped us to explain equilibrium constant and the autoionization of water, which led us to understand the pH scale, acidity and basicity of acids. This is all I'm trying to say. These two would always give you 14. So if you put these two concentrations, this is how you get them. Remember, if you put these two 0.1 times 10 raised to power minus 7, one time you will get this. So this is constant for neutral water, for water that has nothing. These parameters are the property of a neutral water. So if we combine it together, neutral water will not be 14. Oh, if we play around with it's based on the learnings from neutral water that this concept was generated to explain the acidity scale that led us to have the pH scale. I hope you're following me. This whole concept, we generated it from autoionization of water, and we used it to explain the pH.
I don't understand, man.
Oh, okay. Maybe after the lecture, you go and listen to the recording. You will understand again. I said this concept, when I showed you the autoionization of water. Autoionization of water, let's look at it. Look at this. This is the autoionization of water. So when look at water on its own, it dissociates to give you this. You know, we told you that this is how we explain it in a simple way. But what actually happens is that water will, after this, when there's an hydrogen atom, it doesn't really, hydrogen ion doesn't stay on its own. From the first Arrhenius theory, what happens is that it attacks a water molecule to form the hydronium ion, attacks another water molecule to form the OH minus. So the only way to explain this concept using the Arrhenius theory, this and this equation are the same. But the only way to explain it is to bring it into this form. Explain so that this is what we know. This is and this are the same thing. This is like an expanded explanation of this. And so based on this, we could write this equation that if this happens, in a balanced equilibrium system where everything is going back and forward and is balanced, and this is what will happen. So we can say we can prove that Ka times Kb is equal to Kw, but that will take a whole long time to do. But I've explained what Ka is. I've explained what Kb is. So if you've understood what Ka is and Kb is, then if we multiply Ka and Kb and balance the equation, you will get Kw. So we can as well say that the concentration of the hydronium ion and the concentration of the OH ion will give us our Kw. That's what I'm trying to explain here. And so that led me, I've explained, I've thought about this, and I think most of you understand this. And so if you use that equation, you can do a lot of calculations. This is a sample calculation we can do. Here, the household cleaning solution of ammonia, we know the concentration. We know the concentration and we are of the OH ion, and we are told to calculate the H minus. So if we do that, what we have to do here, we are told the hydronium ion. They didn't tell us to assume anything. They've told us the amount of OH ion in that solution. Since you know the amount of OH ion, you put it here. W is a constant, so you put it there. Can you not find your H ion? You can. The same thing for this. This one, you know they say calculate the OH ion. You are told the amount of you are told the concentration of the hydrogen ion. So you put it here, and then you find your OH. This is very straightforward. This is very straightforward. The second scenario where I gave you, I told you that the second scenario is this one. It's still the same principle, but here they didn't give you everything. They just told you 1 point something of this. They didn't tell you the amount. They told you find the amount of the pH. They didn't say find the amount of hydrogen ion or OH ion. So here they want you to find the hydrogen ion and use it to find the pH. So you find the hydrogen ion. You find the hydrogen ion is very tricky. This undergoes complete dissociation. So the amount of this will always be equal to this. That's it. And at this point, I've not talked to you about pH. That's why you did. But I told you that pH is equal to minus log of hydrogen ion. So that's why many of you didn't understand at this stage. Maybe when I go back and review this course, I will move this slide to after pH so that there will be less questions. So at this point, I've not taught you about pH, but you can relate to it that pH is equal to minus log of hydrogen ion. You've understood to this point. The only new thing is that pH is equal to minus log hydrogen ion. The same thing for barium hydroxide. The way I was explaining before was more complicated. This is an easier way, which I've solved in the book, the slide. So this is it. See, barium hydroxide here is not exactly like HCl. This one dissociates to give you 2 molecules of hydrogen OH ion. You cannot just assume they have the same concentration because of this. So you now multiply 0 times 2 and 2 times 0.02 to get this. And here, but this is the concentration of OH ion. pH is only measuring hydrogen ion. So when you do it on the scale, it will be 14 minus that of this. And that's what we did here. But you might not have understood it there because I've not explained the concept. The concept is what was explained here. This is what I'm trying. All we applied here is what we used to solve this other question. That in any scale, when you are talking about pH scale, there's always an acid ion, there's always a hydrogen ion, and an OH ion when you're talking of a pH scale. Together, they are equal to 14. pH plus POH will give you 14 in this form. If you are saying log, if you are converting it to the log form, log pH plus log minus OH will give you minus log 1 times 10 raised to power minus 14. So if you say the concentration, if you are presenting it in this way, concentration plus concentration would always give us at equilibrium constant, at equilibrium condition, will give you this. So based on this, you can play around with so many things. Is this concept that we use to solve this? I think I should have arranged, but I brought the cat before the horse. Is this concept that was used to solve this here? So any compound based on this now, you can make some small predictions. Any compound with a smaller pKa would have a larger Ka. Any compound with a small pKa will have a larger Ka and will be acidic. Any compound with a smaller Kb would have a larger Kb. Any small compound with a smaller pKb will have a larger Kb and would be a strong base. So let's look at this. Which acid is weakest here? If you look at this, which one is smallest? It gave us Ka. So the larger the Ka, the stronger the acid. So the smaller the Ka, the weaker the acid. So which one will be weaker? Let's look at which one has a smaller value.
HCN.
Which compound has a smaller value?
HCN.
Correct. It has a smaller value.
HCN.
You are correct. You are correct. Yeah. So that's what that's and is this Brostolores theory that helped us understand this. So because of that, we now have a scale. So Brostolores theory still has limitation. No matter how good you are, there's still no matter how good anybody is, there's still problem associated with that person. So that's what's happening. And no matter how good a theory is, there are still limitations. So the limitation of the Brostolores theory is seen here. The limitation of the Brostolores theory can be seen here. It does not explain reactions occurring between non-protonic solvents. You know, it now explains some gaseous reactions. It explains some non-aqueous solution reactions, but could not explain non-protonic solvents. That is, reactions occurring in solvents that do not have hydrogen. He could not explain what is happening because his definition is still based on hydrogen. Definition is still based on increase in hydrogen loss or reduction in hydrogen ion. Base, you know, its base is something that reduces a hydrogen ion. A base is something that reduces hydrogen ion, while an acid is something that increases the hydrogen ion. It cannot explain reactions between acidic oxide and basic oxide. Cannot explain reactions between acidic oxide and basic oxide. It cannot explain reactions that substances like BF3, ALCL. These you will understand in the next topic. These are called Lewis acid. Lewis acid. But let me not jump my slides. It cannot explain for substances like boron fluoride, aluminum chloride. It cannot explain the acidity and how they're able to donate protons. It cannot account for it. So we cannot explain. It cannot explain reactions like this. So it cannot explain three basic things. It cannot explain three basic things. One, reactions of substances like boron fluoride, aluminum chloride, cannot explain how they're able to donate protons. It cannot explain how acidic oxides are able to exhibit acidity and basicity. It cannot explain reactions in protonic solution.
Give me one too.
Who is making noise?
One person at 500 now.
Please bear with me.
Enter 5 now. Today I just enter.
Please keep quiet, guy. So that leads me on to Lewis theory. Lewis theory came to help us the limitation of.
I better go small though.
Please mute yourself, sir. Please mute yourself. So Lewis theory helps us to overcome the limitations of Brostad-Lewis theory. And I try to summarize it this way. Lewis theory encapsulates the theories, tries to encapsulate, and it explains. So the Arrhenius theory is embedded in the Brostad-Lewis theory. The Brostad-Lewis theory is embedded in the Lewis theory. So Lewis acids are anything that are electron acceptors. Lewis bases are anything that are electron pair donators. Anything that are electron pair acceptors, and anything that are electron pair donators, bases. So with this theory, he was able to expound all other theories and account for the strange reactions of the occurrence, how these substances are able to exhibit acidity or basicity, as the case may be. The advantage of the Lewis theory is that it complements all other methods. It does not, it complements them and further helps us understand all other model and explain things that hitherto we could not explain. So that's about the Lewis theory. So Lewis theory, with the Lewis theory, we now have Lewis acids and Lewis bases, and it explains all of them. Which of these can act as a Lewis acid or base? Of course, I've already used ammonia as an example. So yes, because it will accept an electron and it will give an electron, a pair of electrons. That's why it's a Lewis acid and that's why it's a Lewis base. So, but limitation of Lewis acids and base is that, so I've told you the limitation of Brostad-Lewis theory, Arrhenius theory. Lewis theory also have limitation. So we are waiting for you to come up with a theory that will overcome the limitation of Lewis theory. And somebody among you in my class will do so. We are the scientists of tomorrow. Yes. So these are some limitations of Lewis acid and Lewis acid and Lewis theory generally. Lewis concept gave a generalized idea, including all coordination reactions and compounds, which is not always true. That is, it's saying that everything always coordinates, but it's not true. It's not everything that undergoes coordination. The idea about the relative strength of acid and base is not provided in the Lewis concept. Lewis concept is not in line with the acid-base reaction concept. So it doesn't agree with the way acid and bases just react like that. No. Lewis concept has not discussed the basic behavior of protonic acid like HCl. So these are some limitations of the Lewis acid structure. Some of the things we know about acids and base are by reactions, by studies. People have come to know them. So we are still waiting for some explanations to some things, although we know those ones are acid, things are acids and base, but we could not explain some of them. And Lewis acid that tried to explain the limitations of others still has its own limitation. Anyway, general properties of acids and bases that they change. Acids are generally sour. Acids change blue litmus paper to red. Acids are corrosive to touch. Bases are in taste are bitter. Bases are bitter and slippery and soapy to feel. Bases to taste are bitter and slippery and soapy to feel, while acids are corrosive to feel. They change red litmus paper to blue. They may be corrosive to touch too anyway, but they are generally soapy. So most of our soaps are mild bases. And so we look at some properties, some chemical reactions of acid and base, which you know, so I will run here. Acid reacts with base, acid reacts with metals, acid reacts with base, acid reacts with a metal to liberate hydrogen. Acid will react with carbonates to release CO2. Bases react with metal oxide to liberate hydrogen. Bases react with CO2 to form salt and water. Acids will react with base in a reaction we call neutralization reaction to give us salt. What are salts? Salts have special properties. Salts are in nature. We have salts in nature, and we have salts from reactions. Now, in nature, salts are crystalline, are bulky. Most of the salts are soluble in water, but we have some insoluble salts. Salts can exist in their molten state or in solution. Many salts can transmit electricity. And what keeps them together is that they have electrostatic attractions that holds the ions together. And there's usually a chemical bond between them. Salts are products of reactions between acids and bases. Salts dissolve in water to make solution that could be acidic, basic, or neutral, depending on the type of salt. So we have salt of strong acid and strong base, which will be neutral. We have salt of strong acid, weak base, which will be strong. Salt of strong acid, weak base will be acidic. Salt of strong base, weak acidic. Acid will be basic. We have salt of weak acid and weak. We have salt of weak acid and weak base. They might either be neutral, basic, or acidic, depending on the situation around them. We have what we call buffers. No, I will jump over that. And that leads me to redox reaction. We'll talk about this in our next class. I've overshot my time by 10 minutes. Please forgive me. It's because of exigency of time. Okay, but let me just mention that buffers are solutions that are usually a combination of weak acids, soluble salts or weak bases, and soluble salt combinations. They're usually a combination of many things. Buffers, when you hear a buffer is actually a combination of many things, usually weak acids, weak bases, weak soluble salts or weak bases, or soluble salt combinations. They're just combinations of weak acid or weak base and their soluble salts. So weak acid is soluble salt, weak base and is soluble salt. It's usually a combination. And the thing about buffer is that they resist small changes to pH. They resist small changes to pH. So when you want to keep pH constant, you use buffer solution. At the end of this class, every one of you been able to explain what is an acid based on the Brostolowitz theory, Arrhenius theory, and the Lewis base. In this class, I was able to tell you the limitation of the Arrhenius theory, limitation of the Brostolowitz theory, and the limitation of the Lewis acid. I was able to tell you the things that the advantages or the learnings we're able to take from each of these theories. Thank you very much. See you in my next class on Monday. What time is our class on Monday?
9 a.m.
9 a.m. See you by God's grace. See you by God's grace then. Bye.
Goodbye, ma.
Goodbye, ma. Thank you, mom.
You're welcome. You can take this question.
Marcus, can you share the slide, ma?
Ma, will you send the slides to our course reps or what?
I am not promising that. I'll look for materials and send, but I'm not sending my slides. But I'll share the recording so you have the slide. Yes. So I'm sharing it. Yes, because I'll share the recording. Yes. And the slides on YouTube now, because those on live had it. So yes, I'm sharing it.
Having a chemistry test.
You ask our coordinator. Dr. Ogumbayo.
Never told you that one before.
Thank you, ma.
Thank you, ma.
Thank you, ma.
Why is it finding it hard to end?
What are you coming back? Yes.